Hello, class. In this first example, we're going to look at, does the table of values represent an inverse variation? So when we're talking about inverse variation, we're talking about division. The general form of this equation is y equals k over x, where k is a constant. Constant. X and y are our typical x and y that we've been dealing all semester long. So, well, what does this mean? What does this indicate to us? Well, if I go ahead and really quickly just do a little bit of algebra, I'll multiply it by x on both sides, and this cancels. I get x times y equals k. Now, k being a constant, this means that x times y should always equal the same k. So that's what I'm going to do. I'm going to go through this table one by one, or pair by pair, I should say, and just multiply them. So 1 times 12, that's obviously 12. 2 times 6, that's 12. 3 times 4, and we can really quickly see that all of these multiply to give me 12. Okay, so yes, this is an inverse variation. Okay, go ahead and give the second example a try on your own. All right, so this example is actually a good example to look at because it's not quite obvious right off the bat just by looking at it. In the previous example, we could see pretty quickly, oh yeah, all these multiply to give me 12. Well, it actually so happens to be the case for this one, yes. All these pairs will give you 25.5, so yes, this is an inverse. I'm leaving out my ends today, an inverse variation. All right, so let's look at the next example. In an inverse variation, x equals 10 when y equals 3. Write an equation to represent the inverse variation, then find the value of y when x equals negative 6. So we're going to return to that equation, y equals k divided by x. This is our general form. And we're going to use this initial set of values here. Y equals 3, so it's going to go there. We don't know what k is, but that's always going to be your first goal. Find out what k is. And x equals 10. And this just becomes a pretty simple algebraic equation. Just multiply by 10 on both sides. This cancels. You get 10 times 3 is 30. These were the k's we solved in the previous examples. So that means my general equation is y equals 30 divided by x. So we have our equation. Write an equation. That's done. Then find the value of y when x equals negative 6. We're going to plug in negative 6 for x. 30 divided by negative 6. And that gives you negative 5. And I'll actually box both of these since these are both my answers. There we go. I have 2 example 2's in here. Oops. Oh well. Okay, so let's try this next one. X equals 6, y equals 1/2. So again, use your general form, y equals k divided by x. We're going to set y to be 1/2. And we're going to set x to be 6. Now this one might jump off the page a little bit, but I'm going to solve this using the same thing I did before. So 6 times 1/2 is 3, and that's our k. So that means our equation is 3 divided by x. So now find the value of y when x equals 15. So this is 3 divided by 15. Now this won't be an integer. There'll be a fraction we have to simplify. And that fraction is 1/5. All right. Go ahead and try this problem on your own. Okay, so let's go ahead and look at, I'll choose red. Y equals k divided by x. We're going to throw in y is 2/3. and k over 3. Now, this is actually looking pretty obvious because we have the same denominator, but again, for the sake of practice, we'll multiply by 3. These will also cancel, and we'll get 2 equals k. So our equation is 2 divided by x. And then we'll throw a -1 for the second part of our question, 2 divided by -1, and y is equal to -2. All right, so the properties of a reciprocal or inverse graph. What are the key features of the function f of x equals 1/2? So there's a couple things we're going to have to think back in our minds to when we did this at the end of or at the beginning of the semester. We're going to talk about domain. We're going to talk about range. We're going to talk about vertical asymptotes. We have to remember when we talked about discontinuities. The vertical asymptote was a type of discontinuity. And we're going to talk about horizontal asymptotes. Okay. Now, vertical asymptote was a invisible line that the graph approached but never touched. So the behavior was like this, where we're going up here and down here, and we're like kind of just falling off a cliff. Notice the decline is gradual and then just boom. Whereas here it's kind of a little bit of the opposite. It's immediate and then becomes gradual. This is the behavior to look for when we've got a vertical asymptote, okay? So this vertical asymptote, it appears, is happening at the y-axis. So this would be at x equals 0. And likewise, we can see similar behavior at the x-axis where it's flattening off and it's never going to touch the x-axis, going in both directions. So this was at y equals 0. Well, the fact that these asymptotes exist means that x can never equal to 0. This helps us fill out what our domain is. The domain is all list of possible x values. So if a vertical asymptote exists at a value, that means the domain can't exist there. So we think about our domains almost always started with -infinity. And then since we can't use 0, we'll end the interval at 0. And then we'll pick up right where we left off. The next interval will start with 0 and end with infinity. Remember that parentheses means we don't include this value. Let's look at why we can't include 0. If I were to plug in 0, I get 1 over 0. And if you try to type this in your calculator, you, of course, get a math error. Now, using this same line of thought, the range ends up being the exact same thing. Okay, so these are your pretty standard beginnings of domain range vertical asymptotes and horizontal asymptotes for all problems. We're going to use this as a template to solve all problems that ask about properties of variations of this function. So let's look at an example. Without graphing, determine all the properties of the given function. Okay, again, that was vertical asymptotes. I'll abbreviate that now. Horizontal asymptotes, we'll always figure out those first, and then our domain, and then our range. All right. Now, to do that, we look at this function and we have to think about, we have to reflect back on transformations of functions, because now it's not just 1 over x, it's 1 over x minus 3. Okay? So let's think about it. Now, when we think back to transformations, when we start seeing minuses and pluses, we got to think up, down, left, and right. And so this -3 right here, that is right 3. We've never quite seen a transformation of right 3 in this form. So we got to get used to seeing it now. X minus 3 in the denominator like that will be right 3. If it was plus 3, it'd be left 3. And then this plus 2, that would be up 2. Well, let's think about what that does to the graph. If I'm moving right 3, I'm taking a vertical asymptote that was previously at x equals 0, and I'm moving it right 1, 2, 3. So now it would be along here. So my vertical asymptote is now at x equals 3. And then the horizontal asymptote is being moved up 2. So this would be at y equals 2. And now this especially makes domain and range a little bit easier because the domain, the endpoints of these intervals, I use that term loosely, endpoints, was where the vertical asymptote or the horizontal asymptote begins. So now, since the domain ends at 3, our domain will go from negative infinity to 3, and then 3 to infinity. And likewise, our range will go from negative infinity to 2 to infinity. Go ahead and give this next one a chance. All right, so let's go ahead, look at the transformations first. In the denominator is a left or right movement. This one happens to be left 4, and then right here minus 2, that's down 2. Now, when we list our vertical asymptote, we start with the fact that it's left 4, but remember that's in the negative direction. So my vertical asymptote exists at x equals negative 4, and our horizontal asymptote exists at y equals negative 2. Okay, so domain for these functions, we always begin at negative infinity, and then we go to wherever the vertical asymptote is, that's at negative 4, and then go from negative 4 to infinity. The range, same process, but now with the horizontal asymptote. Start at negative infinity, we go to negative 2, and then we start our new interval at negative 2 and go to infinity. Go ahead and give the exit ticket a try. Thanks for watching.